According to Table 220.84, the demand factor for a multifamily dwelling is based on the total number of dwelling units. Therefore, the total number of apartments can be used to determine the demand factor, which is 0.23. The optional calculation method for sizing the service conductors and substation transformer is based on the total building load. Since there are 3 buildings, the total load needs to be calculated by adding the individual feeder loads for each building. To calculate the individual feeder load for each building, multiply the total load for 30 apartments by the demand factor for 30 apartments. The formula for individual feeder load is total load for 30 apartments multiplied by demand factor for 30 apartments. To calculate the total building load, add the individual feeder loads for all 3 buildings. The formula for total building load is individual feeder load for building 1 plus individual feeder load for building 2 plus individual feeder load for building 3. Once the total building load has been calculated, the service conductors can be sized using the following formula. Service conductor size in kilovolt amperes is equal to total building load in kilovolt amperes divided by voltage in volts multiplied by 1.25, which is the diversity factor. Similarly, the substation transformer can be sized using the following formula. Substation transformer size in kilovolt amperes is equal to total building load in kilovolt amperes multiplied by 1.25, which is the diversity factor. Based on the optional calculation method, the total number of apartments should be used to determine the demand factor for sizing the service conductors and substation transformer. However, the individual feeder loads for each building still need to be calculated to determine the total building load. Let's delve deeper into the optional calculation method and explore its nuances. We will examine the process step by step, ensuring clarity in understanding the formulas and their application. Firstly, understanding the demand factor is crucial. The demand factor is a ratio that represents the maximum amount of power that is likely to be used at any one time compared to the total connected load. It acknowledges that not all electrical devices within a building or dwelling unit will be operating at their maximum rated power simultaneously. Therefore, the demand factor allows for a reduction in the calculated load, leading to more appropriately sized service conductors and equipment. Secondly, the optional calculation method provides a simplified approach to determining the service load for residential buildings, particularly those with multiple dwelling units. It leverages the concept of demand factors to account for the diversity of loads within the building. This method is often more straightforward than the standard calculation method, which requires a detailed analysis of each individual load. To elaborate on the individual feeder load calculation, it's essential to have accurate data on the total load for 30 apartments. This total load would encompass lighting, receptacle outlets, appliances, and any other electrical equipment within those dwelling units. The demand factor for 30 apartments, as indicated in Table 220.84 of the National Electrical Code, is 0.33. This means that only 33% of the total connected load is expected to be used simultaneously. Thus, the individual feeder load for each building is calculated by multiplying the total load for 30 apartments by this demand factor of 0.33. Moving on to the total building load calculation, this step involves summing the individual feeder loads for all 3 buildings. This aggregated load represents the total amount of power that the substation is expected to supply to the entire complex. It's important to ensure that all feeder loads are calculated using consistent methods and data to maintain accuracy. Now, let's examine the service conductor sizing formula in more detail. The formula states service conductor size in kilovolt amperes is equal to total building load in kilovolt amperes divided by voltage in volts multiplied by 1.25, which is the diversity factor. Here, the total building load, expressed in kilovolt amperes, is divided by the voltage of the service. This division yields the current that the service conductors must be able to carry. The diversity factor of 1.25 is then applied to account for any potential future load growth or unforeseen circumstances. It is important to remember that the calculated service conductor size represents the minimum required capacity. It is always advisable to select conductors with a slightly higher capacity to provide a margin of safety and to accommodate any future expansion. Similarly, the substation transformer sizing formula is substation transformer size in kilovolt amperes is equal to total building load in kilovolt amperes multiplied by 1.25, which is the diversity factor. This formula is used to determine the minimum required capacity of the substation transformer. The total building load, again expressed in kilovolt amperes, is multiplied by the diversity factor of 1.25. This calculation ensures that the transformer is capable of supplying the entire building complex with sufficient power, even under peak load conditions. In conclusion, the optional calculation method provides a practical and efficient way to size service conductors and substation transformers for multifamily dwellings. By utilizing demand factors and diversity factors, this method allows for a reduction in the calculated load, leading to more cost-effective and appropriately sized electrical systems. However, it's crucial to ensure that all calculations are performed accurately and in accordance with the National Electrical Code to maintain safety and reliability. Now let's clarify a few points that are often sources of confusion. When referring to Table 220.84, ensure you are using the correct demand factors based on the total number of dwelling units served by a single feeder or service. In the provided scenario, since all three buildings are powered by the same substation, you can use the demand factor corresponding to 90 dwelling units, which is 0.23 for the overall substation and service conductor sizing. However, when calculating the individual feeder loads for each building, you must use the demand factor corresponding to 30 dwelling units, which is 0.33. This is because each building is served by its own individual feeder. Another important consideration is the voltage used in the service conductor sizing formula. Ensure that you are using the correct line-to-line voltage for your system. For example, if your system is a 208/120 volt system, you would use 208 volts in the formula. If your system is a 480/277 volt system, you would use 480 volts. Using the correct voltage is crucial for accurate calculations. The diversity factor of 1.25 is a common practice in the electrical industry to account for potential future load growth in unforeseen circumstances. However, it's important to consult with local codes and regulations to determine if a different diversity factor is required in your specific jurisdiction. Some jurisdictions may have specific requirements for diversity factors based on the type of occupancy or the specific electrical loads being served. It is also important to consider the ampacity of the conductors selected for the service conductors and feeders. The ampacity of a conductor is its current carrying capacity, and it must be sufficient to carry the calculated load. Refer to the National Electrical Code Table 310.15b16 for the ampacity of various conductor types and sizes. When selecting conductors, be sure to account for any directing factors that may apply, such as ambient temperature or the number of conductors in a raceway. These directing factors can reduce the ampacity of the conductors, so it is important to select conductors with sufficient ampacity to account for these factors. Furthermore, ensure that all overcurrent protection devices, such as circuit breakers and fuses, are properly sized to protect the service conductors and feeders. The overcurrent protection devices should be sized no larger than the ampacity of the conductors they are protecting. This will help to prevent overloads and short circuits, which can damage equipment and cause fires. Remember to consult with a qualified electrical engineer or electrician to ensure that your electrical system is designed and installed in accordance with all applicable codes and regulations. A qualified professional can help you to accurately calculate the loads, select the appropriate conductors and overcurrent protection devices, and ensure that your system is safe and reliable. Finally, document all of your calculations and design decisions. This documentation will be helpful for future maintenance and modifications to the electrical system. It will also be required for permitting and inspection purposes. Be sure to keep your documentation up to date as the system is modified or expanded. Let's clarify some additional aspects of applying Table 220.84 in practical scenarios. When dealing with mixed-use buildings where residential units are combined with commercial spaces, you cannot simply apply Table 220.84 to the entire building. You must separate the residential load from the commercial load and apply the appropriate demand factors for each type of occupancy. For the residential portion, you would use Table 220.84 based on the number of dwelling units. For the commercial portion, you would use the standard calculation method or other applicable tables in the National Electrical Code. In situations where there are significant electric heating or air conditioning loads, it may be necessary to adjust the demand factors accordingly. Table 220.84 provides a footnote that addresses this situation. It states that if the electric heating or air conditioning load is a significant portion of the total load, the demand factors may need to be adjusted to account for the increased load diversity. This adjustment should be based on engineering judgment and a thorough analysis of the specific loads involved. When sizing the service entrance equipment, such as the main service disconnect and the metering equipment, be sure to consider the available fault current at the service entrance. The available fault current is the maximum amount of current that could flow during a short circuit condition. The service entrance equipment must have a short circuit current rating SCCR that is equal to or greater than the available fault current. This ensures that the equipment can safely withstand a short circuit without failing. To determine the available fault current, you will need to obtain information from the utility company or perform a fault current study. A fault current study is a detailed engineering analysis that calculates the available fault current at various points in the electrical system. The results of the fault current study can be used to select the appropriate service entrance equipment with the required SCCR. When installing the service conductors, be sure to follow all applicable codes and regulations regarding conductor installation. This includes requirements for conductor support, protection, and separation from other conductors. The National Electrical Code provides detailed requirements for conductor installation in Chapter 3. It is also important to coordinate the service entrance location with the utility company. The utility company will typically have specific requirements for the location of the service entrance, the type of metering equipment to be used, and the grounding and bonding of the service. Be sure to communicate with the utility company early in the design process to ensure that your service entrance design meets their requirements. Remember to consider the impact of energy efficiency measures on the electrical load. Energy-efficient lighting, appliances, and HVAC systems can significantly reduce the overall electrical load of a building. By incorporating energy efficiency measures into your design, you may be able to reduce the size of the service conductors and equipment, resulting in cost savings. However, it is important to accurately account for the reduced load when performing your calculations. In some cases, it may be beneficial to install a smart meter at the service entrance. A smart meter is an electronic meter that can measure and record the amount of energy consumed by a building. Smart meters can provide valuable data for monitoring energy usage, identifying potential energy savings, and optimizing the operation of the electrical system. The data from a smart meter can also be used for billing purposes. It is also important to consider the impact of renewable energy sources, such as solar photovoltaic PV systems, on the electrical load. If you are planning to install a solar PV system, you will need to coordinate with the utility company and follow all applicable codes and regulations regarding the interconnection of the PV system to the electrical grid. The PV system can reduce the amount of energy that the building draws from the grid, but it can also introduce new complexities into the electrical system design. Be sure to consult with a qualified solar PV installer to ensure that the PV system is properly integrated into the electrical system. Finally, remember that the electrical system is a critical component of any building. It is important to design and install the electrical system in a safe and reliable manner. By following all applicable codes and regulations, and by working with qualified professionals, you can ensure that your electrical system will provide many years of trouble-free service.